So in the general form of oscillators, we were speaking about Z1, Z2, and Z3. So those three are going to play a major role in deciding what oscillator we are going to use. Other than this amplifier is a common emitter amplifier with voltage divider bias, so which you have R1, R2 voltage divider bias, you have collector resistance RC, and emitter resistance and bypass capacitance we have. So these are going to be the general design of a common emitter amplifier. CC1 and CC2 are used for coupling purpose, and you see output again is taken and fed back to this reactive feedback network and given as input to your base. So here I'm assuming Z1, Z2 are inductors, and Z3 is going to be a capacitor. Z1 is going to be L1, Z2 is be L2, and Z3 is going to be C. So in the Hartley oscillator shown, Z1 and Z2 are inductors, Z3 is a capacitors. You know R1, R2, RE provide the necessary biasing for the transistor to operate in the Q point. The Q point we always fix exactly in the middle of your DC load line, because it has to be always there for proper amplification of your signal. So C is a bypass capacitor, and C1, CC1 and CC2 are coupling capacitors, which are used for effective coupling of signal from and to the amplifier. So the feedback network consists of L1 and L2, which are in series, which is in parallel with C. So this L1, L2, and C will determine the frequency of oscillation of your RT oscillator. It is very beautiful to see that the frequency of oscillation will not depend on any of the transistor parameters R1, R2, RE, CE, RC, CC1, CC2, VC. See how beautifully it is going to depend only on the completely on the feedback network consisting of two inductors L1, L2, and C. Okay, so when the power supply is switched on, you have in the base, you have noise signals which are fed to the amplifier. It is amplified, again fed back to this reactive network. Again, it is fed back to the base. Again, it is amplified. So these oscillations grow until A beta equal to 1. So if A beta equal to 1 or A beta is slightly greater than 1, the oscillation sustain and give a constant output at a particular frequency, F naught. So here you see the midpoint of L1 and L2 is grounded, and across which you have the capacitor connected. So this ground can be common to the ground which you have in the common emitter amplifier. Okay, so if terminal 1 is positive with respect to 3, you know that 1 is input and 3 is ground. So if this terminal 1 is positive, terminal 2 will be negative, because you know that this transistor is going to offer, common emitter amplifier is going to offer a phase shift of 180 degrees. So if you have a positive polarity at terminal 1, 2 will always be negative. And this 2 is again negative, and this 1 is going to be again positive. So the total phase shift is 180, 180. So it is going to be 360 degrees. So the phase difference between 1 and 2 is always 180 because of the common emitter action. So the total phase shift is 360. You have 180 for this common emitter amplifier. This 180 is also reflected across the feedback network. So you have one more 180. So if you look at this loop, 180, 180, you have 360-degree phase shift, which is the condition to be satisfied for sustained oscillations. And we always have this A beta to be adjusted to 1 so that the circuit will act like a perfect oscillator. So the two Barkhausen conditions are satisfied. So this circuit is going to generate efficient sinusoidal